Hey everybody. Today we're talking about area as a limit. We've already seen how to approximate the area under a graph using rectangles. I'll throw a link to that video up top here. For instance, take the function f of x equals 2 minus 1/2 x squared on the interval -1, 1. We're interested in the shaded area here on this graph. Our approach is to divide that interval into equal pieces, say n equal pieces, and then draw rectangles that are sitting on the x-axis, whose heights are defined by the heights of the graph at the right-hand endpoints of each of the subintervals. Here's what the picture looks like when n equals 4. I've divided the interval -1, 1 into 4 pieces to get subintervals of width delta x equals 0.5. And then the heights of the rectangles are going to be the value of the function at all the right-hand endpoints. So f of -0.5, f of 0, f of 0.5, and f of 1. And then we can compute the area of those rectangles as an approximation of the area under the graph, doing the height of the function at the right-hand endpoint times the width of the rectangle, repeatedly, in this case 4 times. Now, just by the way that we've constructed this, the rectangles all have the same width, so we can factor out that delta x, in this case that 0.5. Here, if we evaluate all of this, we get about 3.625. We can generally improve this estimate just by using more rectangles. Let's write a general expression for the area under the graph approximated using n rectangles and right-hand endpoints. So if we let delta x equals b minus a over n, the total width of the interval divided by the number of rectangles, we're going to get the quantity a sub n equals f of a plus delta x plus f of a plus 2 delta x plus f of a plus 3 delta x, and so on, all the way up to f of a plus n delta x, that whole quantity times delta x. Written more succinctly, the sum from k equals 1 to n, f of a plus delta x, f of a plus k delta x times delta x. Of course, a is the left-hand endpoint, and b is the right-hand endpoint here. Now that formula looks like a bunch of gobbledygook if you don't understand what it means. So it's very important to keep the interpretation in mind. A plus k delta x is the right-hand endpoint of the kth subinterval. And therefore f of a plus k delta x is going to be the height of the kth rectangle. Then f of a plus k delta x times delta x is the area of the kth rectangle. And of course the sum of all those is going to be the total area of all the rectangles. Unless the function f of x is very badly behaved, like a sort of function we don't run into in Calc 1 or 2, then these approximations get better and better as n increases. And so it makes sense to define the area under the graph of f of x between x equals a and x equals b just as a limit of that previous expression, as the number of rectangles goes to infinity. And obviously, this definition only makes sense when that limit exists. One warning here, when the graph of f of x is below the x-axis, the area is going to be counted as negative. In essence, this definition is going to view the rectangles as having negative height at those x values. Okay, let's do some examples. Example 1. Using a limit, write an expression for the area under the graph of y equals 1 minus 1/2 x squared between x equals -1 and 1. So this is the previous example that we did in the finite case of n equals 4. In this case, delta x is 2 over n. We have an interval of width 2. We're dividing it into n pieces. And the area is going to be the limit as n goes to infinity of the sum f of -1 plus 2k over n times 2 over n. So there I've just substituted in the values a equals -1 and delta x equals 2 over n into my formula. Now let's replace f with the actual function 1 minus 1/2 x squared. To get the limit as n goes to infinity, sum k equals 1 to n, 1 minus 1/2 quantity, -1 plus 2k over n, quantity squared, all times 2 over n. Now, it is possible to evaluate this limit algebraically using properties of summations, but it's a real pain in the butt, and we're not going to go through it right here. Example 2. Using a limit, write an expression for the area under the graph of y equals sine of x between x equals 0 and x equals pi. Again, don't evaluate the limit. In this case, the interval has a total width of pi, So delta x is going to be pi over n. Taking the formula for the area as a limit and replacing f with sine, a with 0, and delta x with pi over n, we get this limit. Limit as n goes to infinity, sum k equals 1 to n, sine of k pi over n times pi over n. Just to add a little bit to our graph, I here have drawn in the first few rectangles. You should imagine each one of these having width pi over n and height k pi over n, where k is indexing the rectangle that you're on. So k equals 1 is the first rectangle, k equals 2 is the second, and so on. When you're doing these problems at first, I really do recommend making detailed graphs, because the formulas that we're writing down really just reflect the geometry. And understanding the geometry will give you a much better chance of writing down the correct formulas. One final example. The following expression represents the area under a curve on some interval. Determine the function and the interval. Limit n goes to infinity, k equals 1 to n, square root 4 plus 5k over n times 5 over n. So right away we see this has the same form as the limit definition of the area under a graph, which, just to refresh our memory, is right here. We can clearly see that our delta x is that 5 over n, just by the structure of our formula, and it sure looks like the function is just a square root. Next, we can see that since the inside of our general formula is a plus k delta x, and the inside of the function that we have in this particular problem is 4 plus 5k over n, probably we should just go ahead and take a equals 4. Now that we know our delta x and our a, we can solve for b. Since 5 over n is b minus a over n, and a is equal to 4, we're going to get b equals 9. Okay, so let's just wrap up by having an interpretation of what we've just found. This limit that we've written down represents the area under the graph of the function f of x equals the square root of x on the interval 4 to 9.